Welcome again to Online Geometry. Tonight we're going to talk about Section 6.6, Properties of Kites and Trapezoids. So we have two different shapes we're going to talk about here. We'll start off with the kites, move on to trapezoids, which is going to end up being the bulk of what we talk about. So there's lots to do with trapezoids. So just a quick little deal, objectives. We're going to start off by using some properties of kites to solve some problems, and then we're going to move on to properties of trapezoids, specifically looking at some isosceles trapezoids. Lots of vocab tonight. These vocabulary terms, some of them are not listed on your sheet because they're things that technically have been covered in previous classes, but if you need to add them in, I'd add them in just to the left-hand column there. So like kite, if you don't remember what kite is or you didn't know, just add it onto the left. Same thing with trapezoid and whatnot. We'll have some diagrams just to help you guys out with that stuff. So starting off with a kite. Kite is, of course, a quadrilateral because everything we're talking about right now is a quadrilateral. It's got exactly two pairs of congruent consecutive sides. So we've got, it's kind of like a rhombus in that we got the consecutive sides congruent. The difference is that there have to be two separate pairs that aren't congruent to each other. So you can see AB and AD are congruent, which gives me one pair, and BC and DC are congruent, which gives me a second pair. But we can't have AB and BC congruent. That doesn't work. It's no longer a kite. Then it becomes a rhombus instead. So we have to kind of maintain that two separate sets of sides that are congruent. So that's a kite. We do have a couple of theorems about kites. The first one says that if a quadrilateral is a kite, so if we know it's a kite, then its diagonals are perpendicular. So just like a rhombus, which has perpendicular diagonals, a kite has perpendicular diagonals. We get the nice little set of right angles there in the inside where the diagonals intersect. Second set, the second theorem, quadrilateral is a kite, then we have a pair of opposite angles congruent, but only one. We can't have both pairs congruent because then we end up with a parallelogram and we have a kite instead. The trick is figuring out which one it is that's congruent, and I would say that the easiest way to see is look at your pairs of sides that are congruent. You can see AB and AD are congruent, and BC and DC are congruent. The angles that are congruent, B and D, highlighted here in blue, they're the ones that are in between your two sets of sides. So the ones that are not included between congruent sides. So not A and C, which are made up of congruent sides intersecting, that they're the ones where the non-congruent sides meet. Okay, so let's use it real quick. You see this picture on yours. We know that we have kite, EFGH. It tells us it's a kite. We're given two angles. We know that FEJ is 25 degrees, and we know that FGJ is 57 degrees. So we're going to go ahead and stick those on our figure first. I'm going to go and label those. FEJ down here is 25, and FGJ down here on the right is 57 degrees. Then I'm going to look and say, okay, I know it's a kite. What do I know about kites? Well, I know my diagonals are perpendicular to each other, just like a rhombus. So let's stick that little box there in the middle. I got all right angles there, which makes it nice because now if you look carefully at this kite, it actually could be four little triangles, four little right triangles, in fact. And on two of them, we already have one of the other angles. So like if you look at this triangle here, FEJ, we have 25 degrees, we have 90 degrees from the right angle, and we're just missing this one here. So we go ahead and just do 180. So this triangle's out to 180. I subtract 25 plus 90, what I have so far, and I get 65 left to go right up there. So I got 65 degrees there. Do the same thing to this triangle here on the right, triangle FJG. I know that I have 90, I have 57, so I'm just going to do 180 minus whatever 57 plus 90 is. It gives me 33 left to put right there on the other side of F. So that means the total angle there ends up being 65, and 35 is 98 degrees, which looks about right. Now, the really cool thing about kites is that once we've got this much, we actually have here at EG, right across the middle, that diagonal, forms a line of symmetry with the kite. So it's exactly the same on one side of the kite as it is on the other side. So really, now that I've got the 25 and the 65 and the 33 and the 57, I can just take all those and flip them down to the bottom and put them in the exact same spots down there too. So all I'm going to do is draw a whole bunch of arrows. I'm just going to say the 25 also goes down here, the 65 also goes down here, the 33 also goes here, and the 57 also goes here. So all I'm doing is taking the top half and moving it down to the bottom as well, because we have a nice little line of symmetry with kites. Kites are nice like that. Okay. Moving on to trapezoids. Little basics of trapezoids first. If you don't remember what a trapezoid is, it's a quadrilateral, of course. It's got exactly one pair of parallel sides. So it has, we call those bases, the top and the bottom, or the left and right, depending on which way you're looking at it. And those sides that aren't parallel we call legs. So here's a little diagram here. You can see that the top and the bottom have the little arrows for parallel. They're bases. And the sides are called legs that aren't parallel. And then if you look, we have two pairs of angles, and we're going to pair them up. And you'll see that there's a reason for this in a minute. We're just going to kind of arbitrarily call them base angles. So we have a pair of base angles up here because they're on the same base. A pair of base angles down here because they're on the same base. You wouldn't say that A and B are base angles because they don't share the same base. B is on the top, A is on the bottom. So it's just kind of giving you a label to say that these up here go together and these down here go together. And again, it gives us a label to talk about them, which is going to be important here in just a minute. But first, we got to talk about the one special type of trapezoid, the isosceles trapezoid. Now, we know isosceles triangles have two congruent sides, so it makes it isosceles. So isosceles trapezoids are the same thing. They're trapezoids that have two congruent sides. Specifically, it's the legs we're talking about. If the legs are congruent, then it's an isosceles trapezoid. And we got three theorems to go here. And it's not really three theorems, but we're going to kind of condense it down to just three. The first one says, if we know we got an isosceles trapezoid, then our pairs of base angles are congruent to each other. So if we have an isosceles trapezoid, then if you look here on our picture, B and C are congruent, and A and D are congruent. So the ones along the same base are congruent to each other. And most of the time, that's going to be pretty obvious which one you're talking about. You could obviously kind of look at the picture and say, well, A is acute and B is obtuse, so I'm not going to say A and B are congruent. I would say B and C are congruent. And if you look, there's the parallel side, so yeah, B and C share that same base as a side. Second theorem. If a trapezoid has a pair of congruent base angles, then it's isosceles. So kind of going backwards and saying, I'm not sure if it's isosceles, but hey, look, I got base angles that are congruent, so it's got to be isosceles. It's just not quite the converse, but essentially the converse, what we just said, just going backwards. And then 665, the last one, is a 2-for-1. It works both ways. It just says that the diagonals of isosceles triangles are congruent. So if you've got those congruent diagonals, then you know that the trapezoid is isosceles. And if you know the trapezoid is isosceles, then you know that it's got congruent diagonals. So it's kind of like a rectangle with the congruent diagonals there. Only we don't have two pairs of parallel sides, nor do we have any right angles. So let's take one last thing, one more definition before we do our example. Mid-segment of a trapezoid. We talked about triangle mid-segments last semester. A triangle mid-segment, just to refresh your memory, is a segment that goes from the midpoint of one side of the triangle to the midpoint of the other side of a triangle. The trapezoid mid-segment, almost the exact same thing, only specifically it's talking about the legs. So the midpoint of one leg to the midpoint of another leg. So you can see you got a midpoint right over here on the left, and it goes to the midpoint right over here on the right. That's a mid-segment. It connects the midpoints of the legs. And we have a theorem about it. It says that mid-segment has two properties. One, parallel to the bases. So XY here is parallel to BC and to AD. It's parallel. You can see it looks pretty parallel, but it is. The second one is that it's the average of the lengths of the bases. So if you were to take your lengths of the bases and average them, meaning you add them up and divide by 2, you get the length of the mid-segment. It's kind of exactly halfway between them, and it's exactly halfway between them in terms of length as well. Distance and length both. So what does that mean? How does that translate to a problem? Well, let's look. Here's the diagram you have on your page. You don't have to find EH. I'm just letting you know that's what we're doing. We're going to try to find this base down here at the bottom, this little bitty skinny one. We know we have a trapezoid mid-segment. We know that the 16.5 here, XY, is mid-segment because X is a midpoint, and Y is a midpoint. So it means it's a mid-segment because it connects midpoints. We know that the other base is 25. So what we're going to do is use our trapezoid mid-segment theorem. We're going to take that theorem and we're going to write it out first. We know that XY has got to be the average of FG and EH, whatever EH happens to be. So I'm going to write that kind of fancy style. We say that XY equals half of FG plus EH. So you add those up and divide by 2. Okay. Now we're going to throw in the parts that I know, the 25, the 16.5. So sub in those values, so I get 16.5 is half of 25 plus something. You can put an X in there if you'd rather put an X in there. So then I start solving, working backwards. I know that here I have half of this, and I could distribute that half if I wanted to, but I'm not. Instead, I'm going to multiply both sides by 2 to get rid of the half, which lets me on the left-hand side, the 16.5 times 2 is 33. And then that half kind of cancels out to either 25 plus EH, just this part here. So it cancels out that divide by 2. And then I'm just going to subtract 25 from both sides to finish solving, and EH ends up being 13. So 16.5 is the average of 13 and 25. And that's how we find our trapezoid mid-segment. Hopefully, if you guys have any questions, please know that you need to let me know when you get to class tomorrow. Just say, hey, Mr. Olivier, I really didn't understand what you meant by this, and I'm more than happy to go over it with you guys.